Okay, so today we're still in chapter 3. This is actually the last part of chapter 3. And in chapter 3, remember we're numerically summarizing data. And today we're going to pick up right where we left off last class, and we're looking at measures of position. So what we're looking at, it's just looking at, trying to write and talk, or write and talk at the same time doesn't always work out well. Measures of position, what we're looking at is where a data value is located compared to the other data values, right? And that's what we really spent a lot of time on last class, talking about that. And we're just going to keep going with that. So our data position. And with our data position, last class, we left off with talking about percentiles. Remember, I said we're not going to calculate percentiles, but it was just the knowledge of what a percentile is. And remember, like I gave an example, if we had the 40th percentile, that means 40% of the data values are smaller than that one data value that's at the 40th percentile, and 60% are higher or larger, more than that data value. So just with that knowledge, we're going to move on to quartiles. And quartiles are just special situations or a special case of percentiles. And we are going to learn how to get these, and we will use these actually often right now. So quartiles are just points that divide the ordered. Remember, it's an ascending order from smallest to largest. I'll write that here. Data into 4 parts, so into quarters. That's the name, quartiles. So what we're looking at is if we have our data values all lined up, and we had the minimum value over here on the left and the max value all the way over here on the right, then right here in the middle would be what we actually, I think it was like the very last thing I talked about, which is quartile 2, which is the median. So remember I said, well, the median is a special case of a percentile where it gives me, it's right in the middle, and 50% of my data is smaller than that number and 50% is greater than that number. That's also called my quartile 2. So another name for this could be the 50th percentile. So the median has a lot of names. Okay. And right here, we would have quartile 1, and up here, quartile, oops, I almost wrote 3 again, 2. And I want you to recognize that we have 25% in between each of these. So 25% of my data is here, 25's here, and 25's here, and then 25's up here. So it makes up my whole data set. Okay. So we'll just make a quick note. Quartile 1 just is my 25th percentile. And that just means 25% of the data is less than this number, and 75% is more. That's all that means. Quartile 2, which we just talked about, is the median. That's the 50th percentile. And we have 50% less and 50% more. Hope that's clear. when I'm kind of skipping around. Quartile 3 is the 75th percentile. See, there are special cases of the percentiles. And it says 75% of the data is less than this value, and 25% is more. Okay, so those directly relate to percentiles, and they're just the special cases. I have to make a note, and I don't know where I want to do it because I'm out of room, but I want to do it on this page. I'm going to write it over here, I guess. Let's make a note about quartiles. So quartiles are far from the min and the max. So the smallest or largest values. And since I feel like I need to, there we go, maybe. I don't know if that really helped. And since they are so far, they are what we call resistant to outliers. This is so important for us. Remember, when we're talking about these outliers, these are my unusual values or extreme values. Just so we recall what those are. So what I'm saying here is quartiles are far from the smallest and largest. And look at where they are. Look at quartile 1, 2, and 3. They're in the middle, right? Here, and then my smallest, my largest are out here. And so what I'm saying here is that since they're so far from that min and the max, they're what we consider resistant to outliers. So what this is saying, and I'm going to show you in an example, if this max number is right here, or if it's a larger number all the way out here, this quartile doesn't care. It doesn't change that quartile. And same with quartile 2 or quartile 1. It just cares that there's an actual number there. It doesn't care what the number is. So it doesn't care if the number is 100 or if the number is 1000. So if you have an outlier like 1000, I'm just throwing numbers out there. I don't have an example to tell you right here, but then it's what we call resistant when it doesn't affect. It's not affected by these outliers. And I'll try to show you an example real quick here when we look at one. Hopefully I remember to throw it in there. So when we have these quartiles, we have something called an interquartile range. And the interquartile range, I never write it out, just that once, it's IQR. So I might say it, but most of the time I even probably say IQR. So for the interquartile range, this is, it's going to be used as a measure of spread, and I'll get to that in just a second, but let's get to the formula of it. IQR is just equal to quartile 3 minus quartile 1. So it's just the range. It's just the range of this middle section here. So it's just telling you how the range of these numbers between quartile 3 and quartile 1. So a lot of times we use this. We can be used for data that is not bell-shaped. I'm not saying it has to be not bell-shaped. I'm just saying it can be used for data that's not bell-shaped. This is a measure of spread. So remember, when we were talking about spread last week, we were looking at range, which was the max minus the min. And then we really started getting into standard deviation, which was that really long calculation, but it gave us a really nice number, and the number represents a lot and it means a lot to us. And that's the one really we use the most. And now we have another measure of spread, which is called the IQR. And it just tells us that middle section. You can't see what I'm pointing to, this middle section here, that range of those. So it's a measure of spread. And remember, just recall that the median is the measure of center, right? That's the measure of the center, which we typically use for non-symmetric or not bell-shaped data, but we can use it for symmetric. It's just the mean should be pretty close if it's symmetric, okay? So this is my interquartile range. So I want to actually find the quartiles of a data set. So let's take a look at an example and we'll find these values here and we'll work through that. Now, I'm going to show you how to do it by hand, and you are welcome to do it by hand, but just know for a large data set, by hand isn't the greatest. But we can also do it using our technology, and you'll see that when you work on your daily assignment or your team assignment rather this week, okay? Let's take a look at an example. So the example here, I have data values. That represents the amount of money, I'm going to say in dollars, spent on junk food. Last Thursday by 20 students in my pre-calc class. Now I don't have pre-calc this semester, so this was a different semester. Okay. And I feel like that's way too zoomed in. Messing with my camera. All right, so let me give you this data that I collected. Now this is going to be called raw data when you have all these just different numbers. Nothing is organized. I will organize it for you. I'm just going to give you the data as I received it. Okay, there we go. So here's my 20 data values from my sample of my 20 students from my pre-calc class, okay? So now here I want to find quartile 1, quartile 2, and quartile 3. So the very first thing I need to do this by hand is I need to actually write it out in order. So I need to write my data values in ascending order, so smallest to largest, and I've done that already, so I'll go ahead and do this. I already organized it. I'll just separate them out by commas so there's no confusion. Just kind of spaced them out too far in the beginning. All right, so here they are ordered in ascending order, smallest up to largest. Hopefully I didn't miss any of my numbers. I didn't double check. So what I want to do first is I'm actually going to find quartile 2 first. I'm just choosing this one. You're going to see why in a minute. It's kind of the easiest one to find first. So remember when we calculated the median? That's quartile 2, right? So we already know how to do this. So since n is 20, which means it's an even number, then I'm going to take n divided by 2 and n divided by 2 plus 1. So that's 20 divided by 2 and 20 divided by 2 plus 1. So it's the 10th and 11th data positions. I'm going to average them, right? Okay, so right here, this is the 10th and 11th, right? So I'm not averaging 10 and 11, I'm averaging the 10th and 11th. So I'm just going to take 5 plus 7 and divide it by 2 because I'm just finding the average here. And I get 6, right? So my quartile 2 is 6. I'm just going to box that so it stands out. So I have that information in a minute. Now I'm going to go ahead and find my quartile 1. So I could do this a couple different ways, but what I typically do is I separate my data into my lower half and I kind of ignore my upper half. Well, I've already done that by doing my quartile 2, right? Right here is the middle, right? So this is my lower half, and now I'm just going to go ahead and find the median of the lower half. Does that make sense? You would do the same thing if you had an odd number. It's just that middle number would be the middle. So now what is my n, right? So it should be 10, right? Because I had 20. So I have 10 below and 10 above. So now that I have 10 for my n, I'm going to look at n equals 10 now for the lower half. I just like to write it all out in case anyone wants to look back at their notes and find out where the heck I got 10 from. Looking at n divided by 2 again and n divided by 2 plus 1. So I'm looking at the 5th and the 6th data values, and I'm going to average those together. So 5 and 5, 5th and 6th. So here I'm just going to take, and I don't have to write this out, I'm writing it out in case anyone needs to go back and look. And 5 is my quartile 1. We're going to look at this in a number line too. I think it's really nice to see. Then I'm going to do my quartile 3 next. I'm going to calculate that one next. Remember, quartile 3 is on my upper half. So I'm going to do the same thing. I don't really have to do this again, but I can. So I can think about this in 2 different ways. I can think it's for my upper half 10 values, I'm looking at the 5th and 6th number, right? So I could say, okay, well, it's the 5th and 6th numbers here. Or since I had a lower 10, I can add 10 to the 15, the 5 to get 15 and 10 to the 6 to get 16. Does that make sense? And then I can count from left all the way to right to get the 15th and 16th. So we can go either way with that. And this is only when you're doing it by hand. So here, again, I'm going to average them. I know I don't have to write this down. I know we all know this, but again, I like to show you all the steps in case anyone looks back. So right there's my 3 quartiles. So all you're doing is you're finding the median over and over and over again, right? 3 times. For the median, the actual median of the data set, the median of the lower half, and median of the upper half. So maybe I'll just write that down. This is like the median of the lower half. And this is the median of the upper half. And maybe that kind of resonates a little better. Okay. So let's take a look just on a number line if we were just visualizing this, what this looks like. My smallest value is 3. My largest value is 21. My median, right in the middle is 6. Remember, my quartile 2 is right here. I'm sorry, my quartile 1 is 5, and then my quartile 3 is right here at 10. So what this says is I have 25% in between each of these. And it's just nice to have that little visual right here, right? And then you can kind of see, okay, the lower half, right? People spent between 3 and 6, and the upper half between 6 and 21. I mean, there's a lot bigger range here than there is here. And then my interquartile range, just for fun, we'll look at the IQR, which is quartile 3 minus quartile 1, which is 10 minus 5 is 5. So what the interquartile range says is that the middle 50% is between $5, and $10. So it gives us an IQR of $5. Right? That's my middle 50%. Has a range of $5. That's not a real big range, right? When we're talking about this. So that's finding the quartiles. And like I mentioned, we're going to do this like this one time right now in class with a simple, small example. And then when you're working with your teams, you're going to try out your technology. Remember, I give you instructions on those for your calculator and for Minitab. If you're working with Excel, it's really not that difficult. You could probably Google it to find out. I just don't provide you instructions on that. And same for like if you use R, I don't know R, or Jump. But Jump's, I think, fairly similar to Minitab. You could probably figure it out. Okay. All right. So that's doing it by hand. It gives you an understanding. You're finding the median over and over again, right? We're looking at that median. So when we find quartiles, we can do more than just know that they're special percentiles, okay? We could do more with them. And the first thing we have is what's called the 5-number summary. And that 5-number summary is a very specific order of numbers from this data set, okay? So it's the min value first, and then second, it has my quartile 1, then it has my quartile 2, which I'm just going to put in parentheses so we all remember this is the median. Then it has the quartile 3 listed, and then the max. So if someone says, oh, here's the 5-number summary, you're getting this, right? You can visualize your number line and what's going on. You could actually just look at it and say, oh, my IQR is the difference between quartile 3 and quartile 1, right? But actually we can do more with this. So let's apply the 5-number summary using this example here. So let's just say, let's use the same example and actually look at the 5-number summary, which is right here ready for us. So as above. Okay. So my min number is 3. Then my quartile 2 is 5. Median is 6. Quartile 3 is 10. And max is 21. So when I have my 5-number summary, it's the same thing as visualizing it in this way on the number line. Someone tells you the 5-number summary, you know it's always in this order. It's not like in a jumbled order. So a 5-number summary means that your data set has been summarized for you in a specific way with the median, the minimum, quartile 1, 2, and 3, and then the maximum. So if I give you a 5-number summary, you don't need to find your quartiles because they're there, right? 5, 6, and 10. It's already given to you. So we have to know what that means because sometimes I'll give a 5-number summary and then people still try to find the quartiles. It's like, it's done for you. It's organized. I've already summarized the data for you, okay? And when we follow from a 5-number summary, we actually have a graph that goes along with this. And I'm talking about a different graph than just this number line. It's actually called a box plot. So the box plot is just a graph of the 5-number summary. Okay. So I'm going to show you this. I'm going to show you a generic box plot where everything is located, and then we're going to apply it to this example using these numbers here. So we're going to do 2 of them right now. So for the generic box plot, and I'm going to go through the steps of how you would start, and then we'll apply it in the example. So for a box plot, you normally have some kind of a scale. And it's down here like a horizontal scale, okay? I don't have like numbers to follow through. I'm just showing you something generic. So I'm just going to draw a line with no numbers on it whatsoever. when you're drawing a box plot, you always start with your quartiles first, your 3 quartiles. And you actually put them where they belong on the number line. And you're going to draw 3 vertical lines where quartiles 1, 2, and 3 are located. So I'm just going to put them some random place on this number line because I don't actually have information. And then you're going to connect them with the box with horizontal lines. So this right here is my quartile 1. This is my quartile 2, which is the median. And then this right here is my quartile 3. So there's my box. Then from there, I'm actually going to make a note of where my mean is. My mean, not the median. I know where the median is. It's this middle line. So I want to actually add the mean. So I'm just going to put a little like key code over here for our graph. And what it is, it's a plus sign with a circle. This is equal to the mean. So what I want to do is I want to get the average. Remember, that's what the mean is, the average of all the data values. Now, we should know by now, after a couple classes ago, that when I have a mean and I have a median, I can tell a little bit about my data set, like the shape of it, right? Based on my mean and median. So if the mean is the same or smaller or larger than the median. So I want to be able to put that on. I'm just going to throw it on here somewheres. I don't know. I don't have an actual data set that I'm following. So it would go in there, inside your box, wherever it lines up. Okay. So now I need to find where we have any outliers. So remember we talked about outliers now for the past few classes. These are my unusual values. I don't want to include them in my graph the same way I would include all my values that aren't unusual, okay? So I need to make sure I look at my outliers, and these are going to be with a little asterisk. But I have to look at a calculation first. So I have to know how to find my outliers, okay? So outliers are any values more than what we call our upper fence, which that is equal to quartile 3 plus 1.5 times the IQR. So I have a calculation there for that. Okay. And then I have or values less than my lower fence, which is equal to quartile 1 minus 1.5 times the IQR. And what that calculation does right there for me, it tells me if these values are far enough away from the rest of the data for me to consider them to be unusual or outliers. And we're going to mark those separately with an asterisk. Now, I don't actually have data values in front of me, right? So we're just going to pretend we have something maybe over here like that. Okay, I'm going to put it there wherever it belongs. Okay, so I've just marked it on my box plot. Okay, so when you're doing this, you'll actually compute that and you'll find if in your data, if you have any values outside there. Then what we also have is we have what we call whiskers, and that's like these little horizontal lines. And this is part of my graph, the whiskers. And this shows me where all my data values go. I'm going to do it in a different color just so we have it. So my data values would go there, and my data values maybe go all the way down here. Okay, the whiskers show how far out my data values go. So right here, and I want to make a note that over here, this is the minimum value that is greater than the lower fence. So your lower fence would maybe be here. Okay. This is my lower fence. Okay. Then the same idea up here on the upper side. This value where this ends is the max value less than the upper fence. So what it is we're figuring out where our fence is, and that's the upper and lower fences, and anything outside of those fences are marked with asterisks for outliers, and then inside are considered normal data values. But I don't want to put my whisker all the way to the fence because maybe I don't have data values out that far. I just have data values wherever they are for my raw data. So I want to make sure I, make a note of that. I also want to note that just like before, 25% of my data is here, 25% of my data is here, and then 25% is right here, and 25% is over here. So you can see the breakdown of your entire data set, looking at all the values, 100% of the values, and where it all breaks down. Okay, so this is called a box plot. This is the graph of the 5-number summary. So this looks kind of weird because I didn't apply it to any numbers. So let's go ahead and try it with an example and apply it to some numbers, and hopefully it makes a little bit more sense. And we can see if we have any questions from that. So we're going to take the same idea and just apply it to our example. So we're going to look at this example here. We're going to use the same example. I started writing same and example together. That's what happens when I talk as I write. All right. As above, we know. Okay. So the 5-number summary, I'm just going to write so I don't have to keep showing this other page. The 5-number summary is 3, 5, 6, 10, and 21. And I want to draw a box plot. Now, we don't always have to do these by hand after today. We can use our technology, but I don't really know if it's any easier or quicker using our technology, to be honest, with these. Okay. So like I mentioned before, I have some sort of a number scale to base everything off of. So my minimum number is 3 and the max is 21. So I need the scale to at least go 3 to 21. I'm actually just going to start at 0 here, and I'll probably just count by 5s. Try to make it consistent like that. So 21 is right here, right beyond, and I need to have 3, so right there. You could pick whatever scale you want. I'm not picky about a scale. It's just as long as you have some sort of scale for me to read, because you don't typically label a box plot above the values. I mean, you could, but you don't typically do that. Okay, so the very first thing I'm going to do is I'm going to draw vertical lines for my 3 quartiles. So it's 5, 6, and 10. So right here at 5, and then again at 6, which is somewhere around here, and then at 10. So right here, I have my box, right? So that's a big chunk that done. I'm going to skip the mean right now because I don't have that, I don't think. Oh, I do have it. I wrote it down the side. So I'm just going to do that over here, that the mean is equal to 7.65. So I might as well just throw that on there right now. So 7.65. So this was representing 6. So 7.65 is somewhere around here for my mean. Okay, so I want to draw my whiskers, right? I want to move forward, but I have to look at the outliers first. I need to know what those are. So right now I need to do some calculations for my lower and upper fences first. So for my lower fence, that is quartile 1 minus 1.5 times the IQR. So I'm just going to make a note off to the side about my IQR over here. So IQR is equal to 10 minus 5. So it's 5. Okay, so I have that number right there, which I think I already wrote it before, but that's okay. So I have my IQR. So I'm going to just plug into this. Quartile 1 is 5 minus 1.5 times 5. Okay. This is going to leave me with a negative number, and that's okay. So this just leaves me with negative 2.5 when I calculate that out. So that's my lower fence. I'm just going to put that on here, over here, because negative 2.5 would be over here somewhere, and I just mark it like that. So I'm going to label it, but you don't need to label it. I'm going to label it so you know what that is. That's my lower fence. Now let's take a look at the upper fence. I have to calculate that as well. So my upper fence is quartile 3 plus 1.5 times the IQR. Again, we already know IQR is 5. So I'm going to just plug everything in. So 10 plus 1.5 times 5. That gives me 17.5. So I'm going to mark that on my upper fence. So it's somewhere right around here in the middle between 15 and 20. So I have my upper fence. You don't have to write what they are. I know what they are when you draw it. I'm just doing this for notes. Okay. Upper fence. I feel like my lighting is just okay. It's just okay. Kind of play with my lighting a little bit here. Okay. Now I can go and see if I have any outliers, meaning if I have any numbers that are unusual for my data set. So remember what I said, an outlier is outside of the fences. So I'm talking about, do I have any data values that go outside of here? So in order to tell this, I can see for my max it is, right? My max is 21, but I need to actually see my raw data to see what else I have going on. So I need to go back to the problem, which is right here. Here's all the data, all organized. And so I want to see what values I have that are beyond 17.5. And if you look at the raw data, I only have the 21. So I'm going to mark right here at 21 with an asterisk, my outlier. And I don't have any other values between the upper fence and the outlier that are also other outliers, right? Because it ends at 15. Now that 15 is significant for me. So remember I said the whiskers go to values that are inside the fence. So for my upper side, my whisker goes all the way to the largest value that is inside that fence. So I need to look up here. Well, the fence would be right between the 21 and the 15, right? So 15 is going to be that next largest number that's inside my fence. So I'm going to put a little point there, and that's where I'm going to draw my whisker to. So I only want to draw the whisker to values that are actually in my data set, right? Because I don't have numbers between 15 and 17 up here in my data set. So I don't want to indicate that I do. And I'm going to do the same thing on the negative side, or on the left side, I should say. It's not negative, it's the left side. And my lower fence is a negative number. That's okay. I know it doesn't make sense unless you return something and you got money back. It doesn't make sense for our data. That's okay. That just happens sometimes. It's stats, okay? It's real life. So things like that don't always work out perfect. So I'm still going to use the same idea that I want to have the next number in line here. So it's the smallest number, but inside my lower fence, okay? I want the very smallest number. So you can see my min is 3. That's clearly inside the fence. So that's where this value goes to. So 3 for a point, and then I just drew my whisker to that value of 3. And that is my box plot, guys. So it's really nice. It's actually, it seems longer and more difficult than it actually is. The hardest part is the calculation, and it's not even the calculation, it's remembering the numbers, remembering what the formula is for the calculation. That's really the hardest part. So I'm going to tell you right now, you will see this pop up on exams. You'll probably see this pop up on a final exam. And I'm going to tell you right now, the biggest mistake is someone drawing their whiskers. It's not even the fences. People get that, right? You guys, you remember it, you write it down like on a little cheat sheet, whatever. It's not that. It's where your fences, or not your fences, but your whisker goes. A lot of people tell me, oh, the whisker goes all the way to the fence. Well, it only goes to the fence if 17.5 was the data value up here. Okay, that's the only time. It's never going to go to the fence unless that data value is included. So it only goes to those data values inside the fence. So we need to make sure we check that out and we don't miss that. I want to talk about one more thing with these box plots. We're going to use these and study these. We actually use these in Stat 2 to get an idea of what's going on with our data. So it's actually a useful chart. We don't use it a bunch in Stat 1, but we do right now when we're studying it. Okay. The box plot's really nice to get an idea of what's going on with our data set. And I want you to remember what I mentioned here, that I have my median, which is my middle line, and my mean, right? And I know what that means. If my mean is larger than my median, I probably have a skewed right data set. So I want to show you just some different box plots and what shape they would represent. And by the way, this one represents a skewed right data set. So I'm going to just show you the different examples of what we could see and the shape that they would go for. So if we had a symmetric, let's just say shape and a box plot, so we get an idea of what they look like. So if we had symmetric, so if we have a symmetric data set, then our box plot will look pretty symmetric. It will look pretty even, meaning my median will be pretty close to the middle. My mean will be pretty close, might not be right on top of it, but pretty close to the median, okay? And my whiskers are pretty even. That would be a symmetric box plot. You might still have an outlier here or there, but that's the general idea or picture of a symmetric box plot. Now, if we were going to have a skewed left data set, the box plot of that data set, I would have my box. And remember what happens with skewed left? I have a whole bunch of little values to the left. So my median, and I'm going to be dramatic, is over here towards the right of my box. And then the mean is pulled down to the left. Probably not that much, but I just like to be dramatic with it. And my whisker on the right is a lot smaller than my whisker on the left. Again, I'm being dramatic with it. So I want you to get the point of where everything is kind of located to one another. Okay. And then the same thing for skewed right. And it's skewed right is just a mirror image of my skewed left. So I have this box. My median is further to the left. My mean is pulled to the right with that skew. I have a longer whisker over here and a shorter one. And that's what we had on this last example, was a skewed right. You could see the whisker on the right was a lot longer than it was on the left. You can see that median is favored over here towards the left side, right? And then the mean gets pulled to the right. So I would definitely say this example was a skewed right. box plot. So it's skewed right distribution of the data. When we're looking at box plots, we might compare box plots. So I'm just going to kind of put this over here because I have some room. So if we want to compare box plots, I have a few things for you to look at. So what I mean by compare box plots, when we're looking at two or more, graphs. So maybe we're studying the amount of money that people spent on junk food for a certain day, but maybe we're studying men versus women, right? Or maybe we're going to study like RIT students versus U of R students or versus MCC students, okay? Like different colleges in the area, something like that. So that's what I mean. We're going to look at different box plots, but we're going to be comparing the same thing on those. So one thing that you can look at and compare between those are the typical value. Remember, the typical value is the center. And when we're looking at this and you're talking about the typical value, you're talking about that median, which is quartile 2. So if you're going to compare two box plots, you're looking at that middle line. Okay. The spread, we can talk about the spread. And when we're talking about the spread, we're going to compare the IQR. Remember, that's the width of the box. So maybe we're comparing these two. It looks like the spread for those two distributions look fairly similar, right? The width of the box looks about the same between those top two. And we want to talk and compare the shape. So we really can't compare the shape as much as saying, one's symmetric, one might be skewed left, the other one skewed right, that kind of thing. So here, when we're doing this, make sure you look at the entire box plot, but we really want to look at the mean versus the median. So I wrote it backwards as what I said, the median versus the mean. And then lastly, do we have any outliers? So when I ask you to compare box plots or to analyze a box plot, these are the things I'm talking about. Look for the median, look for the IQR, look for the shape, and look to see if there's any outliers. Remember, outliers will be noted with a little asterisk. And we could have multiple outliers, right? We could have a couple here. We could have like 3 over here, right? You don't have any, could have 1. So it just depends on your data set. Remember, the outliers are unusual values. Okay. Anyone have any questions for me on this today? I guess I used a lot more time than I thought.